Welcome to part 2 of lesson 26, dealing with scatter plots and linear modeling. We have ourselves a scatter plot here on page 233 dealing with breast cancer mortality in Indiana, ages 50 and under. So I would like you to hit pause right off the bat and try to answer questions 1 through 7. You should be able to do a majority of them based off of lesson 25 and then the first part of 26. So do that. It all has to deal with this graph right here, this graphic, and then come back and check your answers. Make sure you fully understand. Let me know if you have questions. So let's deal with number 1. Write the linear equation which relates Indiana breast cancer mortality and how it relates to time. Well, that is given on the graph, right? So they tell you that y equals negative 0.0014x plus 0.0941. And I want to just point out your slope is negative. And hopefully you recognize that because your line is going down. If your line is going down, we've got a negative trend, a negative slope, right? Everything is negative. And number 2, the scope of the model in years. Well, if you remember, the scope of the model deals with your x-axis, also known as your independent variable, and that goes from 0 to 40. So again, you can see the data stops after 35 years, and because the graph goes till 40, we can make decently accurate predictions for the following 5 years. Number 3, interpret the slope of the regression line. Well, the slope is negative 0.0014. If we put it over 1, it makes it easier to interpret. Remember, y's are on top, x's are on the bottom. What do the y's represent? Well, that's the mortality rate. The x's are years after 1975. So when you are interpreting this, because it's negative, which answers the second question, we know that it's decreasing. So your mortality rate is decreasing by 0.0014 for every 1 year after 1975. So again, it really helps to do this whole y's over x's, because you know slopes change in y over change in x. What do those represent? Identify your independent and your dependent variable. It makes interpreting slope so much easier. Question 4. Find the linear correlation coefficient and interpret it. Well, they tell us on the graph that r squared equals 0.7743. So, to do the math, we're going to square root both sides. So we end up with r equals 0.8799. What's wrong? What did I forget? Remember, we have a negative trend. That means we will have a negative correlation coefficient. So r is negative 0.8788. And what does that mean? Well, it's not super strong because it's not really close to 1. But it's closer to 1 than to 0, or closer to 1 than it is to 0.5. So I would say this is somewhat strong. I mean, it's not super strong or very strong, but it's somewhat strong linear correlation. So, and you could just say it's, kind of, or you can use whatever words you want, as long as you understand that it's not super, super strong, right? It's not dang close to being perfectly linear, but it's better than being dots all over the place. Number 5, estimate the mortality rate for 2001. Okay, so this is where we have to think. In 1975, X was 0. So in 2001, X is, well, how many years after 1975 is 2001? And that answer is 26. So I will use my y equals negative 0.0014. I'm going to plug in 26 for x and then add 0.0941 to it. And when you do that, you end up with 0.0577. So the mortality rate in 2001 is approximately 6%, right, if I change that decimal to a percent. How does this compare to the actual mortality rate? Well, let me go back to the graph here. What did we say? It was 26. So that's this dot right here, this line. So you can see the actual dot is higher than the estimate. So this right here is the estimate. The actual is higher than the estimate. And you get that from the graph, right? So again, we know that using the model is an estimate. Some of them are going to be lower, some of them are going to be higher. That's okay. Number 6, what about for the mortality rate for 2015? Well, again, X is 0 in 1975. So in 2015, we are talking, how many years later? 40. Gosh, I had to think for a minute. 40 years later. And that is just outside the scope, right? We don't know what the actual is because that is not on our graph. But if we look, we can predict because that is within the scope of our model. And when we do that, negative 0.0014 times 40 plus 0.0941, and do the math, and you will end up with 0.0381. So, just a little under 4% is what we would expect in 2015. Now, part 2 of this question of, is this going to be accurate for 2015? Well, accurate, how accurate? Are we talking exact? No, this is not going to be exact. Should it be close? We would expect it to be close, but it's not going to be perfect, right? This is an estimate. Estimates are not perfect. It is an estimate. Number 7. Estimate the absolute change in mortality rates from 75 to 2010. So hopefully you remember, this would be old, this is new, absolute change is new minus old. So I've got to figure out what they are. So when I look at 2010, I estimate my mortality rate to be 0.05. And for 1975, I estimate 0.08. So when I take new minus old, I get 0.05 minus 0.08, and I get negative 0.03. Does it make sense that it's negative? Why, yes, Becky, of course it does, because it changed and it went down. So yeah, it should be negative. Oh my gosh, you're so good. Of course. So yeah, that makes sense, right? And yes, I have officially lost my mind. Letter B, approximate the relative change. So again, we know that we have for 2010 is 0.05 and 0.08. So you found your absolute in the top, dividing by the old, which is 0.08, and we get negative 0.375. So what does that mean, right? Remember, so we can change this to a percent and say we had a 37.5% decrease in mortality rates in Indiana for people under the age of 50 from 75 to 2010, right? That's a decent increase. I'm happy with that, considering I'm in Indiana and I'm under 50. That makes me feel good. And part C of that, which measure of change would you share if, right? Because remember, in class, all the time we talk about absolute and relative change. Depending on who you are and who you're talking to, will depend on which one of these values you're going to share. So if you're hoping to implement a new experimental treatment, you want to show that we are not making strides. Things are not going well. We need to try something new and crazy, right? This is where you would use absolute. Oops, can't spell there. Because the answer was negative 0.03. That's a small change. You can say, what was that? 35 years, we only had a 0.03. That was the change. It looks so small that people are like, yeah, you're right. We need something new. Rah, rah, rah. Well, that we know that's not necessarily true. If we're throwing a benefit for cancer survivors, then you would say it's decreased 37.5% in 35 years. Look at the changes we are making, right? Then it sounds like we're doing good and whatever we're doing is working. So depending on what you're trying to sell, who you're trying to sell it to, totally, right? And this is the same data showing the same information, but look what it can do. So very, very, very different. All right, let's turn to page 34. Once again, I would like you to hit pause and try to answer the questions 1 through 7, then come back and check your answers. Notice how this one is positive, right? Goes up. So we have a positive linear correlation. All right, so hit pause and try it. Number 1, which variable is dependent upon which, according to the graphic? So which variable is dependent? Well, that would be degrees Celsius are dependent upon the concentration of CO2 in parts per million. Because we know that dependent is the Y value, and so the Y value is dependent on the X value. Number 2, write the linear equation. Well, they give you that on the graph again. So Y equals 0.0101x plus 10.716. Again, notice my slope is positive, and even without looking at the equation, we could have known that just by looking at our line, right? Because our trend line, it goes up. If it goes up, there's an increase. If there's an increase, there's a positive slope. So let's interpret this slope. I mean, why wouldn't we? What else are we going to do, right? We're having a good time. So again, Y's are on top, X's on the bottom. The Y's are the degrees in Celsius. The X's are the concentration in CO2 in parts per million. And it's positive, so it's increasing. So your degrees Celsius is increasing by 0.0101 for every 1 concentration of CO2 in part per million. Okay. 4, use the linear model to estimate the average when it's 400 ppms, right, part per million. So that means X is 400. So when I plug that in, Y equals 0.0101, plug in the 400, and I get plus 10.716. And that's going to give me a Y value of 14.756 degrees Celsius. So if we have a CO2 concentration of 400 parts per million, then we have approximately 15 degrees Celsius. Right? Okay. Linear correlation coefficient. And use this in a statement regarding whether there is a relationship between the average global temperature and the atmospheric concentration. Basically interpret it, right? Find it, tell me what it means. So if I know, based on my graph, it tells me R squared is 0.08426. By the way, I know that you're thinking right now, how do I find this R squared? Like, where's this number come from? Well, if you use Excel, because we all know Excel is fantastic. If you use Excel and you type this data in, Excel will create a beautiful scatter plot, and then you can hit a button and it'll create a trend line, and then you just hit another button and it will bring up the equation and R squared. So really, all you have to do is type the data into Excel and then hit the right buttons, and it will magically appear. It's pretty fantastic, actually. Okay, so sorry, I got off on a little tangent there. But to find our linear correlation coefficient, we take the square root of both sides, and I end up with an R value of 0.9179. Now, stop and think. Is this positive or negative? Well, when you look back at that graphic, it's increasing, right? It's going up left to right. So because it's going up, it's positive. My R is going to be positive. And now we have an R of 0.9179. So you got to stop and you got to ask yourself. And you've got to look inside. Well, yeah, it's pretty strong, right? I kind of think anything above 0.9 is pretty good in terms of strength. So I would say there is a strong, I don't know if I would say very strong, but there is a strong positive linear correlation. You know, it's not superbly strong. It's not up in the 0.8, 0.98, 0.99, but 0.92 it's pretty strong. So I'd say it's pretty good. Can we use this linear model to estimate the CO2 concentration when the temperature is 14 degrees Celsius? I think I need a picture for this one. All right, so I just add this picture quick. Now, we know the scope of the model is all about the X value. So when you look at 14 degrees Celsius, which is here, right, that's a Y value. Well, if we just go that across, does it make sense that we could find values for that? And this is where I say, yes, that totally makes sense, because we have data already around that. So because we already have some data that's around 14, it fits in the terms of my X values. If you would be asking me about 18 degrees Celsius, right, 18 is way up here, that is not anything, and I don't have any data anywhere up there. So that wouldn't make sense. But 14, I have data already there. So yeah, I think it makes sense to do that. You know, it's harder to check when you're dealing with Y values because that's not considered part of the scope. It's all about the X values. Now, number 7, we could talk about this for 75 years, right? Is there climate change or global warming, and explain? You know what? Here's my answer. I don't know. And from this graph, correlation does not mean, or you could use predict, causation. So just because we sometimes see a difference, right, there's a positive correlation between concentration of CO2 in parts per million and degrees Celsius, that does not mean that CO2 in parts per million causes higher temperatures or global warming. It could, but this doesn't prove anything. Correlation does not mean causation. Those are two totally different things. So make sure that you are careful, and if you are looking at data and you see that it has a positive linear correlation, that you don't jump to, oh, then this is what it means. No, it just means that linearly there's a positive correlation. That's it. All right, that is the end of lesson 26. Thanks for playing.